Hi everyone. So for this video we're going to be focusing on rates of change, and you've probably seen some of this before, but we're going to be looking at a slightly different light. So we're going to be talking about velocity first. So here it says, suppose you want to calculate your average velocity as you travel along a straight highway. If you pass mile marker 100 at noon and mile marker 130 at 12:30 p.m., you have traveled 30 miles in a half hour. So your average velocity over this time interval is 30 miles over 0.5, so that's the half hour, and that gives you 60 miles per hour. By contrast, even though your average velocity may be 60 miles an hour, it's almost certain that your instantaneous velocity, the speed indicated by the speedometer, varies from one moment to the next. So, like I said, you probably have seen this before. It may look a little different depending on the notation, but typically when we think about average velocity, we usually kind of think of the word slope. Now, we don't use that word because that word slope is usually indicated for or used for linear functions, but the idea is kind of the same. So when we talk about average velocity, we're looking kind of like the same thing, like I said, as slope. So if you recall, slope is y2 minus y1 over x2 minus x1. So just kind of keep that in mind. And so if we're looking here at the definition, it says the average velocity over the interval, and here they give the interval of time 1 and time 2. So if we look at this picture, we can kind of think of it as this is x1, x2 that we normally use, all right, because this is your x-axis. And typically this would be your y-axis. But because of the notation here, notice they use t for time, which normally we use x, and position here, they're using x when normally we use y. So we're just going to kind of use the same notation that's provided here, but ultimately the average velocity over that interval is given by, if we use their notation, x of t2 minus x of t1 all over t2 minus t1. And actually that's very similar, like I said, to what you've seen before. Instead of like x of t2 minus x of t1, you've probably seen, f of x2 minus f of x1 over x2 minus x1. So it's really the slope formula, but we're now using these defined variables because they've defined it over this particular interval with t1 and t2. Alright, so let's go straight into an example here. So it says a rock is launched vertically upward from the ground with a speed of 96 feet per second. Neglecting air resistance, a well-known formula from physics states that the position of the rock after t seconds is given by the function, and here they give us the function, alright, and it says the position s is measured in feet with s equals 0 corresponding to the ground. So now it says find the average velocity of the rock between each pair of times. Alright, so here they're telling us what the interval is. So really, the interval that we're looking at is from 1 to 3 seconds. Now, just like before, like I said, you've probably seen this in previous courses. This is an interval, so this is kind of like your x1 value and your x2 value, right? So if I were to find the average velocity, I'm looking for quote-unquote slope. In order to do that, you need 2 points, right? And so typically when we've done this before, you've had, x1, y1, x2, y2. And so how do I find those points? Well, they've given us the x values, or the interval. So in this case, I'm using x, but it's really t for time. I have 1 and I have 3. Okay, so how do I find those y values, or in this case the s value? Well, you're going to plug it in. All right, you're going to substitute. So if I want to know what the y value is when x is 1, for instance, I'm going to plug in 1 into the s function. So on the side here, that's, if I'm using this function here, that's like negative 16 times 1 squared plus 96 times 1. And if you simplify that, you should get 80. So that's an 80. Okay. And we're going to do the same thing to find the y value here. So we're looking for s of 3. And if you plug that in, I got 144. And then from here, we're going to calculate the average velocity. And like I said, it's very similar to the slope formula. So we're going to do the y2 minus y1 over x2 minus x1. So in this case, it's going to be 144 minus 80 over 3 minus 1. And what do I get? 64 over 2, which gives me 32. And what are the units here? 32 feet per second. So that is the average velocity from when time is 1 second to time of 3 seconds. Alright, so we're going to do the same thing in part B. So remember our interval here now is from 1 to 2. Alright, so if I want to find my 2 points here, well, I already know when t is 1, we found it already over here, if you recall. Okay, so I know that this is 80, but now I got to find s of 2. So if I plug in s or 2 into the s function, you should plug it in. I got 128. So double check those values, but 128 is what I got. And then we're going to do the same thing. So find the average velocity. So I'm going to have 128 minus 80 for 2 minus 1. And that simplified gives me 48. Again, it's feet per second. All right. So what's the next question here? How do we compute the instantaneous velocity at a single point in time? All right, so let's kind of go back a little bit and let's talk about what instantaneous velocity is. We didn't really talk a lot about that. But in this example above here, average velocity gives you, average, how fast you're going in a certain time frame. All right. Now, instantaneous velocity, however, is the speed at your current time. So like in this example, they say, the average velocity was 60 miles per hour. So that's on average how fast you are driving. But if I want to know instantaneous velocity, you want to know how fast you are currently going at that moment in time. And so you would be looking at your speedometer, right? And that's how, if you need to speed up or slow down, that's where you'll be looking. So if we're looking for instantaneous velocity, we're looking for a particular moment in time. And so if we look back here, it says, how do we compute the instantaneous velocity at a single point in time? You haven't learned yet how we're going to do that, but the one way that we can think about it is we want to look at what happens as we get closer and closer to that specific point in time, okay? And so average velocity looks at the position of an object at 2 distinct points. So if we go back and look at this picture, we're looking at the average velocity, let me erase some of this, is, between 2 points, so from here to here, to those 2 distinct points. While instantaneous velocity looks at the average velocities that approach that value. So, how am I going to see what happens, as you approach the value from left or right? So if I'm looking at, if I want to know what this particular point right here, about how fast I am at that particular point, I'm going to be looking at what happens if I get closer and closer to that point. Okay, so how do we compute it? Well, right now we're going to be looking at some values and we're going to look at what happens. So I'm just going to look at what happens as you approach that value from left and right. And we'll talk more about what that means. All right, so let's talk about the difference here. So visually or graphically, what does a difference look like on a graph? We kind of talked a little bit about this, but for average velocity, again, if we look at this definition here, it is a straight line joining 2 points of a function. So that line is actually called secant line. So that represents the slope of that secant line. All right, so if I'm looking at this graph right here, this is my secant line, and when we're looking at average velocity, we're looking at from this point to this point. Okay, so the slope of this line represents the average velocity. However, if we want to know instantaneous velocity, that's when we're looking at a tangent line. So if I'm looking at this graph here, this is a tangent line. Notice it touches this curve at one particular point. And so if we want instantaneous velocity, we only care about that one particular moment in time. And so we're going to be looking at the slope of the tangent line. Okay, so notice average velocity has 2 points, right? And instantaneous velocity, we're looking at 1. So let's take a look at an example. It says estimate the instantaneous velocity of the rock in the example at the single points. All right, well, if you recall, the function that they gave us was s of t is equal to negative 16t squared plus 96t, okay? We want to know what's happening at one particular point in time. So recall, we're going to look at what happens as we approach that single point. So what point are we looking at? T equals 1. So what I'm going to do is I am going to create a table. So I have a time interval versus the average velocity. So we got to look at the average velocity as we get closer and closer to t equals 1. Now remember, you want to go from the left side and from the right side. So if I'm thinking about a number line, for instance, right, we're trying to see what happens as we approach from the left and as we approach from the right. So if we want to know what that is, we got to pick values on both sides. So let's see. 1, let's just pick maybe 2 values on each side. Okay, so on the left side, we could look at the interval from like, I don't know, 1, 0.95. So 0.95 is pretty close to 1. We could also look at something that's a little bit closer, so like 0.999. So if I'm looking on the left side, right, if I'm coming from this direction, 0.999 is very close to 1. And if I think about it coming from the right-hand side, coming from this direction, we need values of 1 that are a little bigger. So, I don't know, we could do, 1.0001, that's very close to 1. And kind of see what happens in this sense. All right, so let's compute the average velocities of each of these. I would recommend you pause the video at this point, calculate the average velocities, and see if you agree with me. Okay, so I have put what I've gotten for the average velocities, and remember, to compute this, you want to follow the slope formula. So remember, I'm just going to briefly remind you that if I'm looking at this right here, you got to find 2 points, right? So x1 is 1, and then you have 0.95 as the other x value. Find those y values by plugging it into the s function. So it will take a little bit of work. So make sure you do that so that you understand how I got these values. But these are the values that I've gotten. All right, so if we look at these, right, and we're going to look at it from both sides. So if I look at it coming from this direction, because remember this right here represents that moment in time when t is 1, right? So if you notice, if I'm coming from this direction here, right, notice it goes from 64.8 to 64.016. So it seems like it's getting closer to 64. If I'm coming from this direction here, it went from 63.984 to 63.9984. So again, it looks like it's trying to get to 64. And so, looking at this pattern, we can say as our answer that as t approaches 1, because remember that's a point in time we were looking at, from both sides, it appears it is approaching, it is, and we can say 64 and put our units feet per second. So as of right now, that is how you're going to try to compute the instantaneous velocity. You're going to look at the average velocity surrounding that moment, that point, and you're going to kind of make a conjecture of what you think it's going to be.